Hello everybody. This is the continuation of my video for section 4.1. If you haven't seen part 1 of this video, please go see it now or none of this will make any sense. Alright, so now that we have the definitions of extrema, both local and absolute, we're going to be able to use those and use derivatives to find said extrema. So we have two theorems that are important in this section, and they are both named. So as I said at the beginning of this course, if a theorem is named, it's probably important. So please make sure you guys know these. I'm going to put them in red, and if you are continuing your cheat sheet, I would say that these are cheat sheet items. So this first theorem is called the extreme value theorem. All right, so I'm going to write it in full, and then I'll kind of explain it to you guys. So it states that a function that is continuous on a closed interval AB has an absolute maximum value and an absolute minimum value on that interval. So it's important to note that when you're using theorems, basically it's saying if you have these conditions, you're able to say this. So I'm going to highlight the conditions because I feel like you guys struggled with that a little bit during the first exam when we had, for example, the mean value theorem. Or did we have the mean value theorem? Anyway, we had theorems. Oh, like the squeeze theorem and stuff. You guys weren't very good at figuring out the conditions, as they're called. So in this case, we need a continuous function. We need the interval to be closed. And I guess that's pretty much it in this case. I'll kind of explain to you guys why the continuous and closed interval is important. So basically what this guy is saying though is if we have a function f of x and it looks like this, let's say this guy is defined from a to b, so that's our closed interval a to b, and let's see here, yep, that's all we need. So it's continuous, the interval is closed, that's all we need. And what it's saying is that some point along here, in particular this point, oh, did my pen just die? That would be unfortunate.
You good?
Yeah. Okay, so my pen just died, but I can keep explaining this. Anyway, so if this theorem applies, then we know somewhere on this interval we achieve our maximum value. So in this case, we have our maximum value here. And our minimum value here. There are local maximums and minimums as we discussed, but we don't really care about those for this particular theorem. So local maximums and minimums are these guys, but right now we're just talking about the absolute max and mins. Okay, so one reason that it needs to be continuous is if I have a graph that looks like, let's say, this guy. So this function is defined from a to b because even though we have a split right here, this closed dot means that's our definition of f of x at that point. The issue is that this would technically be our maximum if we ever hit it. But if we were to like zoom in really close to this graph, this guy is getting closer and closer, but never reaching this point. And because it's getting closer and closer, technically the value is getting higher and higher. And if we continually get higher and higher without ever reaching a point, we can't have a local maximum. Like it's increasing forever. So that's one of the reasons that this theorem requires something to be continuous. That is also similar to why it requires a function to be closed interval. So if I had, let's say, this guy, I'm open at both ends. So at A and B, I'm not defined. We do have a local maximum here, or an absolute maximum here, but our absolute minimum would be right here on this guy. And because that's not technically defined, you don't have that local or that absolute minimum. So those are just examples of how this theorem could fail, or I guess you could not be able to apply this theorem. Okay, so that's that theorem. And then with that, we have what I think is a more important theorem. This one's definitely cheat sheet material. It's called the local extreme value theorem. By the way, extreme value theorem is sometimes written as EVT. And the local extreme value theorem is the focus of this entire chapter, basically. So I'll go ahead and state that for you guys right now. All right, so it says if a function f of x has a local maximum or minimum value at x equals c, and f prime of c exists. Here, let me clarify that. That's f prime of c, so it's important that you guys can tell that that is the derivative evaluated at c. Then f prime of c is equal to 0. So we talked about this in the last lecture. And that's basically just saying if we have a local maximum or a minimum. So let's see here. I'll draw a graph. So at all of these local maximum and minimums, I guess maxima and minima, the slope of our tangent line, or the instantaneous slope of our graph, is 0. So these are little drawings of the tangent lines. And if you look at those, all of those have the slope of 0, right? Because slope is rise over run, and this is rising none. So none over any number is 0. So that's basically what this theorem is saying. It's just saying it really formally. However, it doesn't mean that anytime a function hits 0, actually, let me think. Yeah, no, not every time it hits 0 is it a local maximum or a local minimum. It doesn't have to be. And an example of that is if a function were just like a flat line. Technically, that would both be a maximum and a minimum, which is a confusing concept that we won't really get into. So anyway, that's what this theorem is saying. We'll be Honestly, this is a disgusting problem. Let's see here. How can we rewrite this? Okay, so if you simplify this by combining denominators and moving negative exponents into the denominator, we will get 4 minus 5x to the 2/3. Oh, I lied to you. 4 minus 5x over 3 times x to the 1/3. That's just finding common denominator and then moving around exponents a little bit. However, if you don't feel confident in doing that, you can always use Symbolab, and again, you'll be able to use that on your exam, so I'm not worried about it. Although algebra is an important skill. So we also wanted to, in addition to solving for x, we wanted to figure out where this guy doesn't exist. So hopefully you guys are